On the night of August 27th into the 28th, almost the entire moon will disappear into Earth's shadow. At the deepest point of the eclipse, about 93% of its diameter will be inside the darkest part of that shadow. Only a thin sliver will remain outside, and yet, this will not be a total lunar eclipse. That sounds like a technical detail. It isn't. Because those final few percent matter far more than they seem. The moon's familiar brightness will collapse. Much of its surface may take on a strange copper-red color. And across much of North and South America and parts of Europe and Africa, millions of people will watch Earth's shadow move across the lunar surface. But one question remains: how can almost the entire moon enter Earth's darkest shadow and still never become completely eclipsed? Most of us think of an eclipse as a simple percentage: 50%, 90%, 93%, 100%. The closer that number gets to 100, the closer the eclipse should look to totality. So, at 93%, the difference should barely matter. But it does. Those final few percent change far more than the number suggests, and the reason is hidden inside Earth's shadow. Earth's shadow is not one uniform patch of darkness. It has two main regions. The outer one is the penumbra. It blocks only part of the sun's light, so the moon dims gradually as it moves in. At first, the change can be so slight that you may struggle to see where the eclipse has even begun. Deeper inside is the Umbra, where Earth blocks the sun itself from direct view. This is where the eclipse becomes obvious. A dark, curved edge moves across the lunar surface as more of the moon enters the Umbra. For a total lunar eclipse, the entire moon has to fit inside this central shadow at the same time. On August 28th, it almost does. The eclipse reaches its deepest point at about 4:13 in the morning, Universal Time. At that moment, roughly 93% of the moon's diameter will be inside the Umbra. A narrow sliver remains outside. That tiny miss is enough to keep the eclipse partial, and the contrast should be striking. One small section still receiving some direct sunlight, while most of the moon sits inside Earth's deepest shadow. But that creates a much stranger problem. If Earth is blocking direct sunlight from almost the entire moon, why doesn't that part of the moon simply disappear? Why can it turn red instead? The answer has almost nothing to do with the moon. It comes from Earth. Even deep inside the Umbra, our planet does not block every ray of sunlight. A small amount of light passes through Earth's atmosphere first. The atmosphere scatters away much of the blue light. Red and orange light gets through more easily and bends into the shadow behind our planet. Eventually, that light reaches the moon. Now imagine standing there. From the eclipsed lunar surface, Earth would look like a dark disk covering the sun, surrounded by a thin, glowing red ring. There would be no blue daytime sky around you. The lunar landscape would be dark, while the edge of Earth glowed with sunlight that had passed through the atmosphere around the planet. In a sense, every sunrise and every sunset happening around Earth at that moment would be wrapped into that ring. And the exact shade is never quite the same. Dust, clouds, volcanic aerosols, and other material in Earth's atmosphere can change how much light gets through. making one eclipse darker and another brighter or more orange. That filtered light then crosses the space between Earth and the Moon and falls onto the lunar surface. It is what gives the eclipsed Moon its copper-red color. Once you know where that color comes from, the event stops looking like something happening only to the Moon. The dark curve we see is our own planet's shadow. The red light inside it has passed through our atmosphere. For a few hours, the Moon becomes a kind of screen, showing us two things we normally cannot see laid out so clearly: the shape of Earth's shadow and what our atmosphere does to sunlight passing through it. That is what makes this eclipse more than just a nearly total one. The Moon is not simply getting darker, it is showing us Earth. And the sudden darkness does something else. It briefly changes the Moon itself in a way scientists can measure. Because when the sunlight disappears, the lunar surface starts to cool. The cooling starts fast. The Moon has almost no atmosphere to hold or redistribute heat, so when direct sunlight is suddenly removed, the surface responds quickly. But it does not cool evenly. Fine lunar soil loses heat faster. Larger rocks hold on to it longer. That difference turns an eclipse into something like a thermal scan. NASA's Lunar Reconnaissance Orbiter has used its Diviner radiometer during lunar eclipses to watch the surface cool in real time. During the June 2011 eclipse, Diviner repeatedly measured the same strip of terrain so scientists could compare how quickly different areas lost heat. Those cooling rates can reveal information about the size and density of rocks, the roughness of the terrain, and the physical properties of the uppermost lunar surface. A region that stays warm longer may contain larger rocks or material that stores heat differently from the fine dust around it. A region that cools quickly tells a different story. During later eclipse observations, the same principle was used to probe roughly the top centimeter of lunar regolith. That may sound shallow, but it is the layer directly exposed to micrometeorite impacts, radiation, extreme temperature swings, and the constant weathering of space. Nothing has to land there. Nothing has to drill into the surface. Earth simply removes the sunlight, and the Moon gives away information through the way it cools. For a solar-powered spacecraft like the Lunar Reconnaissance Orbiter, an eclipse is also an operational problem. During lunar eclipses, mission controllers shut down most instruments to conserve energy, while Diviner can remain active to watch the rapid thermal change. So Earth's shadow is not just something moving across the Moon. For a short time, it becomes a scientific tool of its own, which brings us back to that thin, bright sliver. On August 28th, almost the entire Moon goes through this transformation. Almost. That final sliver is what keeps the eclipse from becoming total. But perhaps that is the wrong way to remember it. For a few hours, we will see the shape of Earth's shadow move across another world. Inside, it will be sunlight that has passed through our atmosphere. Below it, the lunar surface will cool as direct sunlight disappears. So, when the Moon changes on August 28th, we will not simply be watching the Moon. We will be watching what Earth does to it, and all of it happens in our shadow.